was indeed generated by an artificial intelligence tool. Like I think it's not really easy, like nowadays, to distinguish from these two images if one of these is real or fake. And actually, my research topic is about how to design a good automatic tool to distinguish pristine from generated content. So this talk is actually based on my paper, the Media Forensics and Deepfakes and Overview, which has actually the award of the Frontiers of Science Award. And the presentation will first describe to you what do we actually mean today with the term deepfakes, and why is detection possible? How can we establish if an image or a video is real or synthetic? I will also present to you which are the major challenges in the area and which is our research direction. And finally, I will describe to you possible future works. Okay, so there has been really a rapid evolution of synthetic content generation. So here you can see all fake images. So all these images were generated using AI, and in particular, they were generated using what are called generative adversarial networks. So the level of realism of these images is really high, and thanks to these tools, you can see how progress has been really so fast. I mean, in 2014, that was the type of image of faces that could be generated, so fully synthetic faces, and only after 4 years, you can see how high resolution and realism has increased. So, I mean, this was also even unexpected to us. And when we were working on trying to detect if an image was manipulated or not using old tools like, like Photoshop, etc., I mean, it was, we could never imagine that we could reach this level of realism in a few years. And this is actually 7 years ago, but now you can even generate such type of content even better. And actually, so these were generated, as I told you, using generative adversarial networks, but now you can also use diffusion models. And diffusion models give you even much more flexibility because you can describe the content of the image that you want to generate, so using a prompt, as I've done in this slide, and then make this generation. And this is really easy. I mean, there are a lot of tools that allow you to generate synthetic content. Just as an example, I mean, this is my PhD student, and he used Hadoop Firefly to modify one of his images. So he just selected an area in his image, then wrote a prompt, and in one click, the image is modified. And of course, so this is something that everybody can use. So it's really powerful. These are really powerful tools, and of course they can be used for fun or to enhance or improve images. But you can imagine they can be used even for malicious purposes. Okay, so this is text-driven image generation, but right now, I mean, you can also do something more powerful, which is text-to-video generation. So again, using some prompt, you can fully generate a synthetic video using really short descriptions. And what you can also do right now is audio to video generation using diffusion models. So let's see if this works.
We were good, we were gold, count the dream.
So you actually start from a single image, and this single image becomes a video, and you can associate audio. So this is really something extremely powerful. And again, the level of of realism is high, and even you should not really be someone who is very much knowledgeable. I mean, you just use available tools online, and you can do this. I mean, there are other examples here of image to videos. And again, you can understand that this AI can be used for whatever, for spreading malicious content over the web. And I mean, and now we know that these videos are fully generated, but if someone posts them online, I mean, it's not really so obvious, right? I mean, you could actually believe to this, or maybe don't know what to do. And in this other slide, I'm going to show you some of the images that some fact checkers sent us in order to understand if they were real or not. I mean, there were some cases like the fire in California or the flooding in Florida, and actually fact checkers sent these images to us and, hey, can you help us? We don't know if they're real or fake. So this is really an important problem, and everybody should also be aware about that, because it's important to know that you should not really believe to whatever content can be posted online. Okay, so let's talk about this. How can we detect if an image is real or is fully generated? Can we detect fakes by visual inspection? This is actually a question for you, so you can you can try to tell me which one of this image, if you have some hints about which image can be real or fake. Those are fake. So for him, both are fakes. For the other, are weird. Okay, let's see. Yes, it's true. This one is actually a fake image, while the other one was real. I mean, it's not so obvious here. You have maybe also a big screen, but on the web maybe the photos are smaller. I mean, it's not really easy. And so let's try to explore better this image. So she said that the earth had something weird. Is there something, some other clues you can understand from this image? Let's do a zoom. Do you find something weird? I can fool you very easily then. Yeah? Right, perfect. She's a very good observer then. There are inconsistencies in the corneal specular highlights. And actually there are papers published in the literature that try to check this asymmetry in the eyes. Together as well as with other asymmetries, like I'm showing to you in a moment. So like here you can see some weird stuff on the ears, or even some weird colors. So there are actually a quite large literature that try to focus on this lack of symmetries, so like different eye color, even if it can be that you have a different eye color in, or maybe, you know, in that case for the woman, she only has one single earring, but also that case it could be also realistic. Okay, so these are like visual or semantic artifacts that do not involve only faces. They could also involve like perspective or shadows, and indeed there could be inconsistencies on the perspectives. I mean, there are also in this case papers that look at these specific artifacts. Okay, and there is a quite large literature on this. So, I mean, one of the first paper on deepfake videos on faces actually was looking at eye blinking and noted that eye blinking was different from real to fake, to manipulated videos. There were also some interesting papers on heart variations. So they actually tried to estimate heart variations from the videos and noted that they were not the correct, like in a real video. And so, I mean, there are a lot of them. As I told you, corneal specular highlights, eye symmetry, shadow illuminations, head pose inconsistencies, and colors. And the main problem of these visual and semantic artifacts, in my opinion, is that, I mean, they're okay, but technology really advances very fast. So I mean, we really see an improvement in terms of the generation, in this case of faces. You can see, different version of style gun, which is again a method that is a generation method is being based on a generative adversarial network. And if you see the progress of these generation tools, you can notice that the level of realism increases a lot. And some artifacts that were present in older models are not present anymore in the newer models. And this also involves like the perspective or the colors. I mean, they are really very well done. So how can we detect then that an image is real or fake? So again, these are two images. How can we understand if one is real and the other is fake? In this case, one is real and one is fake. I can just tell you this. So what we have already tried to work on is not to rely on high-level semantic artifacts, but to look at low-level artifacts. These are invisible artifacts that are related to the generation process of a synthetic image. So let's see what I want to tell you. So if I want to just give a look to how a synthetic image is generated, you actually start from some random noise at the beginning, and then during training, you have a sufficient data set of images that let you generate a realistic image. Now, typically irrespective of the specific architecture we can consider, a synthetic image generator includes a sequence of upsampling operation. So we have a sort of interpolation, and this type of processing that is carried out inside the generation method leaves some specific traces that we can extract from the image and show to you. And I will do this in one moment. So again, so we have this upsampling operations in order to generate the image. So let's try to understand how we can extract these invisible artifacts. So what we did this in 2019. We considered like 5,100 synthetic images. We denoised them. So we removed the noise from, we removed not the noise, but we removed the scene content from the images. So we used the denoiser to obtain a clean image and then made the difference to extract the noise residuals. And then we made an average of these noise residuals. In this way, we estimated an artificial fingerprint, which is a sort of fingerprint of the model that is linked to the generation tool. So we suppressed the scene content and extracted such artificial fingerprint. And this artificial fingerprint is really a sort of fingerprint of the model. So it is strongly related to the specific model that generated such images. If we take this artificial fingerprint and we analyze it in the frequency domain, so we do a Fourier transform of this artificial fingerprint, we can observe that for a real image, the power spectrum is the one that you can show here on the left. For the AI-generated image, the power spectrum shows some specific peaks. And these peaks are actually hints that there were an interpolation process inside the generation model. And we can see them. You do not see the low frequencies because we actually removed the scene content. We don't want to be influenced by the scene content in this analysis. And so you can notice a really different type of pattern in terms of the power spectrum from a real image and an AI-generated image. So even if you don't see any visible clue in the image, indeed there are embedded artifacts inside the image that can be extracted in order to distinguish if an image is real or fake. And what is really interesting is that these artifacts are different based on the specific generation model that you are considering. So here we actually have shown that not only generative adversarial network, but also diffusion models embed this type of artifacts. And you can see that these artifacts are quite different based on the generation model. What is interesting is that not only there are these very strong peaks, but there is also a difference of behavior, especially around the medium frequencies of the synthetic images compared to the real images. Now, this unique fingerprint can actually help you to do what is called also provenance analysis. So you can actually link the image to the specific generation tool that generated it, which is great. And another thing that is interesting, I will show to you in the next slide. So here you can see that we have different generators, latent diffusion and stable diffusion, and then probably you are more confident with Midjourney, which is a tool that is available online and help you to generate synthetic images. And you can see that the fingerprint is actually the same. So the main reason is that the architecture that is behind Midjourney is actually the same as a latent diffusion or a stable diffusion. So you can understand even from tools that are present online by extracting such fingerprints if they are similar to some architectures that was published recently, like this latent and stable diffusion. And indeed, our first work on the detection of diffusion models was trained on latent diffusion, and it worked incredibly well even on Midjourney. And at that time, we couldn't really explain why this happened because Midjourney is closed, so you don't know the specific architecture that was included. But actually, looking at these traces, we could imagine that the architecture present in Midjourney was very much similar to latent and stable diffusion. And okay, so how can we design a good forensic detector? So I've only said that, okay, there are artifacts, even if an image is look very realistic, and but we want actually to detect, to develop a method that can help us to detect real from fakes. So first of all, forensic detectors in general typically provide a global integrity score, like some number that actually gives you the probability that the image is real or fake, and eventually even a localization map. So we also want a map that tells you if part of the image was manipulated. So actually, this depends on the problem, but you can have like a score that tells you, okay, the image is probably fake or not, which is typically between 0 and 1, and then also a localization map if there a local modification was applied. Okay. This is an arms race, and AI is used for generation, and we also use AI for detection. So we use algorithms based on artificial intelligence also to detect such manipulations. And in particular, so what we started to do at the beginning is to work on deepfake videos. Deepfake videos were, I mean, they started around 2018, and there were a lot of algorithms that in that period let you modify a face. So we started to work on such type of manipulations, and we said, okay, let's train a convolutional neural network to distinguish pristine and fake videos in order to learn artifacts. And again, also on about learning-based methods, there are, okay, a lot of possible deep learning-based methods. As you can see, there are even frequency-based approaches and spatiotemporal features, because of course we are considering videos. And so first methods were on supervised detection. So you needed a large data set comprising different type of manipulations in order to train the detector. In case of the images, you also need face tracking and face extraction because you are just interested to the face of the video. And this is the first dataset that was proposed, and we proposed together with colleagues from the Technical University of Munich, and it's Face Forensics++. When we published it, it was the largest dataset, but okay, now you have much more larger dataset. It consisted of 1,000 original videos and 4 different types of manipulations. So face swap, face-to-face, deepfake, and neural textures. And then we actually collaborated with Google AI, which included much more manipulated videos also in this dataset. Okay, so let's see how this dataset was composed. It actually was composed of deepfake videos where there was this face swapping. So you have a source video, a target video, and then the face of the source video is actually swapped in the target video. And this is the face swapping operation. While another type of manipulation is what is called facial reenactment. In this case, you are not swapping the face, so you are not changing the identity, but the expression of the source video is transferred to the target video. So you have actually the source video here, the target video, and the expression of this person is actually moved into this one, and you obtain facial reenactment. While in this other case, you have in this other case instead, okay, sorry, probably there is no, okay. And so in this other case, the face of the source video is swapped into the target video. Okay, so we built this dataset where we have the different target video and source video, and each target video was manipulated using 4 different type of manipulation. So face swapping, face-to-face, deepfake, and neural textures. I mean, at that time, there were not so many methods to do this type of analysis, but we needed to understand even which type of manipulation was maybe more difficult than another. So then we made our analysis, and in terms of accuracy, results were great. And we thought, wait, hey, that seems to be a very simple problem. Because whatever type of approach we are considering for this analysis, and whatever type of manipulations we are including, I mean, the accuracy is always very high. So we were very happy about that, and we said, okay, seems that the problem is almost solved. But indeed, this happens only if you have the specific type of manipulation in training and of course also in test. If we do a sort of generalization analysis, so we train only on face-to-face and test on face swap, then the performance drops to 50%. So everything is perfect if you know the type of manipulation, and this manipulation is present in training. So let's say that at test time, you should know which type of manipulation was used, which is quite not realistic. So everything is perfect again if training and test are aligned. But if there is a misalignment, so you are training on a different manipulation compared to what you have during test, the performance goes to 98 to 50%. And even we said, okay, let's also consider a different data set. This was a data set that Meta AI proposed in 2020, the deepfake detection challenge dataset that was also included in a Kaggle competition. And this was a very large dataset with 20K pristine videos and 100K manipulated ones. And it was very particular because it was created and built using different type of environments and lightning and whatever. I mean, it is really in the wild. And when we trained on our dataset on Face Forensics++ and then tested on this other dataset, again, performance, okay, not drop to 50%, but 60 to 70% are not acceptable numbers. Okay, so this problem can also be seen on images. So if you have a data set of generative adversarial network generated images, like this is a very popular data set that was proposed by a team from Berkeley in 2020, and it is a data set where we have real images and the corresponding AI generated images were generated using progressive growing GAN. And also in this case, we made some experiment. So if we train on one single generator, so on progressive growing GAN, you can see that on the same generator, of course, you have 100% of results in terms of the area under the curve. And the results are still quite good on the family of GAN models. But then if you test this detector on diffusion models, or even on commercial tools like DALI 2, DALI 3, Firefly, and Midjourney, performance drop. Then if you do the contrary and you say, okay, let's train on diffusion models, on the latent diffusion, and test on all the others, then okay, you do not obtain good performance on GAN models, and performance are indeed good on diffusion models, and okay, quite good on commercial tools. So main challenge of in this field is actually generalization, because AI-based detectors learn from a large number of examples, but they actually overfit on these examples, and they are not good in generalizing. So how can we, and of course, I mean, this is important because you don't know what you will find in a real case, and you don't know if there will be another new synthetic generative model. And so how to gain generalization? And there are different methods that you can find in the literature, and I will actually talk you about what are the directions that we have followed in our research. So what we said is, okay, if it is too difficult to generalize to all possible synthetic generative models, let's avoid to rely on fake data during training. And let's try to develop a method that model what is real. So let's model what is real, and let's find fake or manipulated content because it is an anomaly with respect to what is a real model. And I will present to you in the second part of the talk 3 approaches that we have developed in the last few years. Noise print, ID reveal, and Z, and I will show to you in a moment these methods. Okay, so let's start with the noise print, which is a learned camera fingerprint. Okay, so this, so if a synthetic generator is actually able to, I show to you the artificial fingerprint of a synthetic generator. Of course, also real images have a specific fingerprint, and this fingerprint is related to the way the image was generated, and the image is captured using an acquisition system, and then inside you have a demosyking filter because there is a color filter array, and some digital signal processing operations like lens distortion correction, white balancing, and even JPEG compression. At the end you have your image. And even the camera so introduce a specific fingerprint. A fingerprint which is also linked to PRNU. I don't know if some of you is familiar with the photo response non-uniformity noise. This is a noise which is introduced in every image by very very small artifacts, very small errors of the sensor. So actually every sensor is not perfect. Camera processing operation, we actually consider the different type of processing like resizing, compression, possible adjustment. And you can see that the NoisePrint++ extraction is much better than the NoisePrint and can highlight better the anomalies. So we repeated all the process, but we also considered possible editing histories like compression, resizing, cropping, And we again extracted the fingerprint with this more complex architecture. What was really interesting for this was that by manipulating an image like the manipulation I showed to you before, what we noted was that indeed using the online Adobe Firefly tool, it was not only manipulated the cat, but all the block in the surrounding of the cat was manipulated. Can you see the difference between the background and the manipulation? There is actually a different pattern. And this meant actually that not only the cat was regenerated, but the whole block. And even for this image, I don't know if you have ever used this tool of Adobe Firefly, which is this AI generative expand tool, where you can take an image, the original image, and expand it. So you can make it larger, so adding some content that didn't exist. And also in this case, you can see that the noise print is different. We also actually extended this concept to videos, and in particular to deepfake videos. You can see that the extraction is not as good as for images. It's much more noisy. I mean, in 2019, when we did this analysis, it was quite hard for us to collect a large number of videos, of real videos, in order to extract it. But from the heat map, you can, in any case, by focusing only on the faces, you can in any case see that you can extract correctly this information. And then we tried it on a YouTube video. And can you see the black holes on the face of the actor, where there was a swapping between Arnold Schwarzenegger and this other actor, which is Sylvester Stallone, okay? While on the child, I mean, the face is actually clean. And even when you extract the heat map, you can see a sort of mask in the second case for the actor. Okay, so this was one of our approach. Another one is ID reveal, which is an identity-based approach. So the idea, this actually works only for faces. And the idea was this. Let's change completely the paradigm for deepfake video detection. Let's try not to answer to the question, is this video manipulated, but is this the person who is claimed to be? So let's work on what are called the biometric traits of a specific person, so like facial landmarks, head motion. I mean, it's quite difficult for a generative tool to perfectly replicate the biometrics of a person. And we just wanted to highlight these identity-related inconsistencies. So what we did during training we collected, we didn't collect because there was already available a data set of about 5,000 different identities, and we trained our method on such identities. And during test, what we did was actually extract some features from a reference set of real videos of the claim identity, and then compare with features extracted from the test video. And what is good of this method is that you do not need any type of fake videos. You just need a reference of pristine videos. And this is our method ID reveal, where we extracted these 3D morphable features, facial features. We also come up with a temporal ID network, and again with a contrastive learning strategy. And then we tested this method on some examples of deepfakes which were done on Nicolas Cage. For some reason, Nicolas Cage was an actor that everybody wanted to deepfake, so we had a lot of examples. So you can see that the distance between the real video of the test real video and the collection of around 20 videos from Nicolas Cage is very small from real videos. Such distance increases for the deepfakes. And then we have two cases which are really challenging. One is actually not a deepfake. This is an imitator. And even an imitator, I mean, it's hard for an imitator, right, to be perfect in, with respect to all the possible biometrics of Nicolas Cage. And the other one, which was even more challenging, is a deep fake on the imitator. So which was really hard. And you can see that, I mean, it's challenging. What was really an improvement of this method was the inclusion of audio. Audio was really great in terms of how to improve the performance. So we improved this method and expanded to consider an audio-visual analysis. This is a spectrogram of the audio. And we really obtain much better results using in audio and video. I mean, all these identity-based methods are very good, especially on compressed videos or even attacked videos. I mean, I don't know if you have confidence with adversarial attacks, but you can attack also a video and in order to fool a detector. And these methods based on the biometrics of a person are quite robust to this. Another improvement that we have done with respect to this approach was the use of pre-trained language models. This was quite surprising in the sense that we actually used some pre-trained audio models that were not proposed for identity recognition. They were actually proposed for completely other type of audio applications, and they worked incredibly well. So, I mean, we were surprised. We were like, oh, we did a lot of work on trying to understand how to extract the features, but we could use some pre-trained models, which is okay. The powerful of these large language models and vision language models is really great, even for audio. And you can see here how they are good in distinguishing different type of identities and how performance are much better than our first approach, that is person of interest audio, the violet curve. And these large language models, even if you use them for image analysis, so for image synthetic image detection, in particular, we consider the clip for this task. I mean, they are also very good. And in comparison with the state of the art, you can see that even using very few images during fine-tuning, so the red circles, you can obtain much better performance. And this also was very much surprising to us. So we wanted to understand better why they behaved so well. So what we did a sort of comparison with the convolutional neural networks in terms of the scores, and we noted that the score appeared to be almost orthogonal between the two, which means that we're extracting different type of information. So it was important to consider both of them, and indeed some of the most recent solutions try to take the best of these two worlds, like of the clip-based methods and the older convolutional neural networks. And this works also incredibly well in a few shot detection scenario. So over the web, we actually use just a few images for fine-tuning 10 real and 10 fake from a specific generator, and we were able to obtain a very high accuracy. And this was also really a great achievement, in my opinion. Last contribution is, okay, but if we can use only a few, let's go to zero shot. So let's not consider it all like again. Let's consider a zero shot solution. And the inspiration for this last contribution comes from natural language processing, and in particular from text generated by large language models. Now, the text generated by large language models follows a learned probabilistic model, and the real text can be used because it does not follow such model. So suppose that you have a probabilistic language model, like I saw a cat on a plane in this case. So when you start the sentence, I saw a cat on a, you have a probabilistic model that tells you which is the probability of the next word. And what you can do is actually say, okay, But if I have a low probability, so a plane, then there is a high surprise. Then probably this means that the world is not actually generated by large language model, but it is real. And this is the way these models are working. So high probability, low surprise, then it means that it was generated by a large language model. Now, how to translate this idea that was already published for text, synthetic text detection to images? So we actually said, okay, let's change the perspective and let's switch the role of real and fake. So let's rely on a probabilistic model of real images and then detect fake images because they do not follow such model. So like low surprise, it's real, high surprise, it's fake. So the main problem is where to find a good model for real images. And we used a lossless coder. So we actually know that lossless image coding typically build upon a good statistical model of real images. And so we actually considered a typical pipeline of lossless image coding, which actually includes to predict a value of a pixel given its context, and then entropy encode the prediction error. Now, in our case, the problem was that how we had to consider an image probability estimation. So for words, it's easy because we have tokens and we can do the previous token. While for images, we said, okay, let's consider a multi-resolution version of our problem. So let's make the prediction from low-resolution version, just like in NLP tokens are predicted from previous ones. And we have this type of models. And then our detector is actually, our network is trained to minimize the cross entropy between the predicted model and the empirical distribution which is given by the training dataset. So, I mean, that was quite easy. We just considered a lossless encoder, extracted the statistics at average resolution. In particular, we extracted the actual coding cost, which is the negative log likelihood, and the expected coding cost, which is the entropy. So, I mean, just a few features. And then using this feature analysis, we noted that if we look in isolation at these features, they are not much informative because there is also an influence of the content of the image. But if we look at the difference, then you can notice that for fake images, the prediction from the low resolution to the high resolution is less expected. You can see it's more white, and so their difference is much more discriminative. And by comparing with other methods, we also noticed that we were able to achieve good results, even if we actually do not have fake image training set, so there were no fake during training set. We even didn't train on real images because the lossless coder was already trained. And we think, I mean, this was like really, this was published last year, presented in September at ECCB, and what is really, we think it could be a really good path to follow for the future. So, okay, so we actually, let's do some considerations. So modeling real images can really help to generalize to unseen synthetic generators, so not considering fake during training. We also noted that using a multimodal approach, so video plus audio, improves significantly the performance. Note also that audio is really very easy to be generated right now. So you can find a lot of tools online, and so you can even find tools that can help you to synchronize audio with the lips, so they are very easy. And low-level features can be very powerful, but you have to pay attention to the fact that their strength can be reduced if you have like low resolution and low quality data. And this is a problem which is present, of course, over the web. For example, when a fact checker sends us an image and said, okay, let's analyze it, we always go over the web and download the highest resolution, highest quality image. because we know that if you compress it, if you reduce the resolution, these traces can be strongly reduced. And in general, we do never actually rely on one single detector, but we always work and we always try to analyze a case, a realistic case, by considering different type of detectors. Maybe detectors that look at different traces, detectors that were trained in a different way, and then consider the ensemble of such methods. Okay, so let's go now to what are the open challenges. Okay, so in all this analysis, we do not really know, everything is. If you take a photo with your smartphone, probably it will be AI generated because maybe there is some form of enhancement or improvement of the image. So how can we distinguish what is real or fake? Maybe in the future everything will be AI generated. So what is important is how to characterize the malicious intent. Can we understand maybe using the context, using other type of information that the image was maliciously manipulated and not because of some form of enhancement? What is also something very important, and this is again important because when you go to a fact checker, it actually asks to you, hey, okay, you're saying this is fake, why? So they actually want, and of course, explainable solutions. So trying to extract the fingerprints and show them the clues that are related to the synthetic generative process, it's good because you can explain, but there are really a few explainable solutions. And this is also very important, a very important topic that should be better developed. Another important thing is that whenever you try to detect something, you should always take into account that there is an adversary on the other side. So if you are manipulating an image and I know the way the detector is working, I can actually manipulate the image so that to fool the detector. So I can introduce some invisible noise, some adversarial noise in order to fool the detector. And this is something that one should take into account. If I know that, I can actually fool all my detectors because I know how they work and I can modify the image so that they do not work well. Now, the point is that you can fool one detector, but you cannot fool at the same time several detectors. And this is the reason for which you need to work and to develop different ones. There could also be some dataset biases that you should take into account because you are looking at very weak traces. So you should be very careful in when you build your dataset for training in order to push the detector to look at the right forensic clues and not maybe different biases. Like, for example, what is something that happen is that you have a real image during training. You have real images that are JPEG compressed and synthetic images that are not compressed. And so the detector is actually learning these differences in compression artifacts and not the difference related to the fact that you have real and synthetic generated images. So you should really pay attention on how to build a good training dataset. And what also is also difficult is to give a detector that can be already be used easily in the wild by fact checker. It's like there are a lot of tools that you can download over the web from the web, and you say, okay, let's use this tool that tells me if this is real or fake. But if you don't know how this tool were trained, there is, you use them, but you cannot interpret the result correctly because you don't know what they are looking for. And so it's really important. We want to use AI-generated tools, AI-generated detector, but we need to know the way they were trained. Otherwise, the results may be not reliable. So this is something that probably we are still not ready to, to give tools to everybody and make them use. And also the fact checkers, at least the journalists I'm in contact with, they also do not have the basics of machine learning and AI. So it's even difficult to perfectly communicate to them what we mean with a specific score. You know, when you say my detector tells this is fake with 80% of probability, they say, okay, what does this mean? That only 80% of the image is fake? You know, it's also important to communicate well the results and what really we are telling with our method. Okay, I think I'm almost done. Just wanted to thank the funding projects that led me to do all this research and all my collaborators. Thank you.
Okay, any comments, questions? Okay, please.
You started the talk by showing us the Fourier transform, I think, and it looked like it was a great indication of what was fake and what wasn't. So what's wrong with this? Why did you abandon this?
So the main problem of this analysis, okay, you can use it, of course. The main problem is that whenever you compress strongly an image or resize an image, these traces can be strongly reduced. So these peaks can be, so the peaks which are the high frequencies, if you, for example, compress, you reduces these peaks at high frequency. So you not see them as well as, you know, in high quality images. So the main problem of all this stuff is that you are trying to extract a very weak trace from the image. And this weak trace can be reduced even if you are not a malicious attacker, even if you just reduce the quality in terms of compression or in terms of dimension of the image. You can reduce such traces. So in this respect, one should actually consider, for example, over the web to collect all the similar images which have maybe a better resolution or a better dimension, and you can maybe analyze them jointly, which is something that we are doing right now, because the main problem over the web is that images are posted multiple times. And so they actually processed a lot of time, and these traces can be reduced. This is actually the main problem with such traces. So this is also the reason for which when you look at semantic traces, high-level traces, instead these are much more robust to these low-level operations, because, you know, if I am moving or talking in a specific way, this way of talking or moving will not be really changed if you compress the video. And these are much stronger to these, let's say, low-level attacks, but they could also not be attacks. It's just that I had an example, okay, I forgot to show, but the same image that were like, you know, resized, modified over the web, you can see that the detector changes the answer. So at the beginning it says, oh yes, 100% is fake. Then you reduce it, modify a bit the illumination, and then it's rotated, then it's again recompressed, and then so you see we downloaded all the images from the web, and you can see that the curves at a certain point it says, okay, this is real. And so a fact checker can ask you, oh, okay, but you said it's fake, and now you say it's real, why? And this is, in my opinion, right now, the something that for which fact checkers and journalists and people using these tools really should be aware about that.
Okay, any other questions? Okay, I have a small question. I'm not an expert. Let's imagine that, like me, I have my hair color is brown. So if I wear some glass in my eyes, the color, the eye color maybe becomes blue, for example. So this is one case, and another case, I just paint the blue color in the picture. So can the algorithm to distinguish the two cases?
Okay, distinguish if you inserted the lens or if you changed the. I mean, there are algorithms that can distinguish if you painted or not. I mean, not our algorithm in this case, but if it depends on the scenario. So you should actually use the tools that are more likely also related to the specific scenario. So In this case, we didn't actually consider this, but of course, if the reference videos are you with brown eyes and then it's you with blue eyes, yes, it can distinguish this.
Oh, okay.
So yes, in general, it doesn't care. Whatever you do on the manipulated videos, if it is not present in the reference real videos, then it can detect that.
So any other questions? Okay, fine. Let's thank the speaker again. So please enjoy the 15-minute tea break, and please come back at 3:30.